So guys, welcome to our channel, which is self-taught. So as per today's part, we are going to have a brief discussion regarding the topic output current boosting. So let me read out the notes which I have prepared for you, and afterwards we are going to discuss what is what is output current boosting you use in IC regulator, which is LM317. Okay. So output current boosting. The output current boosting of IC regulator can be the output current of IC regulator can be boosted by using current booster boosting. Boosting means increasing using external transistor Q1. Here is the diagram. We can say at the bottom. We can say here is the diagram. So you can take the screenshot for your further reference. Moving ahead. Q is the output transistor. Q is the output transistor, which means it can carry large current. Let the base to emitter voltage to make it on be 0.7 volts. The voltage across VB is equal to the voltage across R3. For small value of I3, IR3, it is also small. Therefore, small voltage across R3. Q is inactive as IL increases, IR3 increases, which increase voltage drop across R3. When this voltage reaches 0.7 volt, Q get active. Now IL is shared by transistor and IC regulator. So IL is equals to IC plus IO. Here we start with the derivation of the formula by how much factor the output current is being boosted. Okay. So IL is equals to IC plus IO. IC is equals to beta times of IB. IB is equals to I1 minus of IR3. I1 minus, so we are writing in whole bracket I1 minus VB on R3. I1 minus VB on R3. Here is the final derivation we can get from the thing is like IL is equals to IC plus IO, beta times of IB plus IO. So here is the final derivation. You can say by moving ahead, we are going to get a final equation as IL is equals to IO 1 plus beta, IO into 1 plus beta minus of beta VB on by R3. So ultimately the conclusion is going to be the load current equation is going to be IO 1 plus beta in whole bracket 1 plus beta minus of beta times of VB on by R3. So output current IO is boosted by the factor 1 plus beta, where IO is the current supplied to the regulator, and IR also increases, and IR also increase output current. Okay. So discussing ahead how does this works. Okay. So here we can see here is the LM317 IC regulator, IC positive voltage regulator, which means across the load the voltage is being regulated in a positive direction. A positive value of voltage is being regulated by IC LM317. Okay. IC LM317 can give a fixed value of IL, which means the current through the load, which can give a fixed value until a maximum limit. It can give a fixed value of IL across the load. So if we want to boost the value of current across the load, we have to use this transistor, which is Q. Here is the connection how this is made. First of all, introducing the circuitry. IR3 is the current through R3. Here is the transistor, which is Q. I1 is the current which is the input to the LM317 IC regulator. IB is the current which is flowing outward from the base of the Q, which is the transistor, and IC is the current which is flowing out of the collector terminal. Here we are getting IO output from the LM317 at the Vout terminal. IL is the load which is flowing through the load. IL is the current which is flowing through the load, and IL is the sum of IC plus IO. Okay. So we have to basically increase the value of IL. To increase the value of IL, we should first of all increase the value of IO. Okay, IC is constant, so we have to increase the value of IO, then IL will be increased because IL is the sum of IC and IO. So we are introducing a transistor here. Let us assume that transistor gets on, which means IC can flow through the transistor and IB can flow through the transistor when the voltage across base and the emitter is 0.7. We are assuming here that let it be 0.7, then only the transistor can conduct. Okay, we are assuming here let the base to the emitter voltage be make it on be 0.7. Okay, So we are assuming here that the 0.7 should be the voltage across the base and the emitter for the transistor to be turned on, and here we can see the voltage which is the base and the emitter is the same voltage which is the which is the same voltage across the resistor R3. So if IR3 is minimum, so to make IR3 minimum, which means if IL is minimum, that load is not consuming much amount of current. If IL is minimum, then IR3 is minimum. Here we are writing this. Here we are done with the notes. For the small value of IL, IR3 is also small. Therefore, small voltage across R3, Q is inactive. Okay. Therefore, Q is inactive. For the larger value of IL, IR3 is greater. As IL increases, IR3 increases, which increase voltage drop across R3. So as the voltage drop across R3 is the voltage drop across base and emitter terminal of the transistor. When this voltage reaches 0.7 volts, Q get active. Q get active means the transistor gets active, because as we can see here, we have written that the on voltage, the voltage which is required for a transistor to get on is 0.7 volts. Okay, so as IR increases, the voltage across base and emitter terminal increases, which means the transistor now is active. And if the transistor is active, we can see that current, the collector current start flowing through a transistor. From here we are going to get I1, IO is equals to I1, IO is equals to I1, and here is IL. So relation of IC, IO, I1 and IL is going to be I1 is equals to IL, and IL is the sum of IO. IL is the sum of IC and IO. Okay. So here we are writing the same. IL is equals to IC plus IO. So here we are introducing a factor which is beta. So beta is being introduced for this particular Q transistor, where beta is the ratio of IC by IB. So IB is equals to, from here we can say that IB. Okay, IB. From here we can see that IB is coming inward, I1 is going this side, IR1 is going this side. So basically IB plus IR3 is equals to I1. IB plus IR3 is equals to I1. IB plus IR3 is equals to I1. So IB is equals to I minus IR3. Substituting IR3 as VB on by R3 by equation V is equals to IR and I is equals to V by R. So the voltage drop across IR3 is equals to VB on, and R3 is the voltage, and R3 is the resistor across which VB on is the potential drop. So IO, how we are getting this IO? Beta is equals to IO minus VB on by R3. As we can see, as I have said earlier, that I1 is equals to IO. So in this equation, we are replacing I1 by IO. So IO minus VB on by R3. So here is your VB on. So beta times of IB, as we can see, IC is equals to beta times of IB. IC is equals to beta times of IB. So we are replacing IC by beta times of IB, and replacing IC by beta times of IB and keeping IO as it is for a particular instance. So we are replacing here IB. So we are getting IB is equals to I1 minus IR3. So IB is equals to I1 minus VB on by R3. IB is equals to VB on minus R3. So beta is equals to IB into IB is equals to I0 minus VB on minus R3 plus IO. Multiplying the opening bracket and taking IO as constant. So IO is equals to 1 plus beta. So minus of beta VB on by R3. So the ultimate conclusion is that IO in the IL equation is getting multiplied by 1 plus beta. The current is being boosted at the input side by 1 plus beta, and thus as IL is equals to IO into 1 plus beta. So same, the boosting is being done at the output side, which is the load current. So hence the current is being boosted. Thank you.